hello everybody. Welcome to Understanding Neural Networks with Triton Robosub and NeuroTech at UCSD. We are very excited to present to you some theory and background in understanding neural networks and also an interactive demo at the end.
First things first, what we're going to talk about today. We're going to basically just go over some features of neural networks, specifically activation functions and loss functions, and then discuss how exactly these neural networks learn through backpropagation. And then from there, we're going to talk about more recent developments with neural networks, specifically image processing with convolutional neural networks and sequence processing with recurrent neural networks.
They all follow this sort of one layer and next layer pattern. To see how this receives input, you just aggregate all of the inputs, just send it to the neuron, just of what a neural network is. We need to give them some terms to feel more solid in terminology. So you have the input layer. Each of those have some weights. This is called the output. It can just be the input for the next layer. So I would call it next. And you can see the arrow. So the thicker the shade, that means more information of the input is being carried over, and the lighter the shade, it means not so much of information is being summed. And if you look really closely, you can see this green arrow. This is sort of the magic sauce of the neural network. This is particularly called the activation function. Now, neural networks has a lot of buzz. That's probably why most of you have heard of it. I would attribute one of the reasons of it that gains so much media attraction is because it has this insane ability to do something called non-linearity. To me, that is the core of why neural networks are awesome. To illustrate this, we're gonna have this, the input space. With this, it's like a 2D representation, and we have a whole bunch of data plotted in this input space. A linear model, generally what they do is they take x1, x2, so 2x plus 3x2 would give you something probably like a line. But if I were to tell you to separate those data points, you would probably draw something like this. And that's essentially what nonlinearity is. Now, there are still a lot of models in the market that are able to plot this nonlinear curved separation line. But what neural networks really excels at is that regular models, they actually alters the input. So instead of receiving x1, it's plotting, say, x squared or something that's not just x. But the problem with this, you might see, is that if you have like thousands of neurons, it gets really intractable very quickly. But neural networks is able to achieve plotting this line even with thousands of neurons. So they are able to do it at scale. And surprisingly, all they need is just one type of neuron. And that's called ReLU. Basically, it's just if the input is above 0, it just plots it directly. And if it's below 0, it squashes down. It's like blocking it from being passed on. The reason it's able to plot this curved line is that all the outputs from the Y space only, so this half of X inputs contributes to all of the outputs in the Y space, yet the other half is squished to this single point. So you can imagine the space being stretched and other parts of input space being squashed. So when you put, after many of this squishing and stretching, and you pass a line to it, in the original space, it's gonna look like a curve. In the actual neuron, it also has this feature. It has this threshold, and if it's under it, it gets completely blocked. So, you can see this sort of biological intuition behind it. And if you look at this particular activation function closely, you can see all this part of X values contribute to almost 80% of the variation in the output space. So it's as if these parts are being stretched in the output space. Whereas if you look at the other parts, so the left and right, even though you can probably see those are more or less like 60% of the input space, in the output space, it only contributes to less than 10% of the variation. So you can imagine the majority of the inputs being squashed down. So now, because so much information is being squashed down, you really need to be careful how much is being squashed. If everything's being, squeezed into a very tight space, when you draw a line to it, it's still going to look like a line in the original space. So one thing to note is that the ReLU function, the derivative of it looks almost like the firing threshold from a biological neuron. So again, you can see this type of intuition behind why an activation function works. And because of the possibility of information loss, you got to be really careful what kind of model, what kind of activation function to choose. So ReLU works well for the most part, but when the model is really long, you have many, like tens of layers, each squashing the input space, then in the end, you might have nothing that gets passed. So some of them are called the leaky ReLU. Even though they squish part of the input space, they still leave a little bit. So in case that might be useful later, they can still be stretched back.
So basically, as we learned previously, activation functions control the flow of information through a neural network. So like Simon was saying, the neural network can learn to stretch information that it deems to be important, and it can squash information that it thinks isn't important. But how does the neural network actually learn to do this? Well, a big part of that, if you are familiar with machine learning techniques, is a loss function. And if you aren't, well, all a loss function does is basically tell the neural network how incorrect its guesses are. There are generally two types of neural networks when they're used to solve a problem. There's a regression network, which is a neural network trying to guess a target value. For example, trying to predict the price of a house given properties of the house. Or classification. An example would be a network trying to distinguish between cats and dogs given images of animals. So with each type of neural network, there are different loss functions associated with them, and there are different sort of pros and cons to each loss function. When talking about regression, the two main loss functions that you'll encounter are mean absolute error and mean squared error. If we take a look at the graph on the left here, when the target output is at 0 here, or at the center of the graph, the loss function states that it has perfectly calculated it and will return 0 loss. On the other hand, if it goes further away from 0, the loss will start to increase. Now, for mean absolute error, it increases linearly. This means that guesses that are pretty close to 0 will still be given some amount of loss, and that amount of loss scales linearly as the guess moves further away from the target output. However, on the other hand, mean squared error, you notice it's a parabolic shape. This means that guesses that are close to 0 will be deemed okay by the loss function. They're pretty close, but they just need a little nudge to get there. On the other hand, outliers, points that are very far away from the target guess, will be deemed extremely bad by the loss function. So this can have pros and cons. On one hand, if we talk about predicting house prices, and the neural network outputs a price of $10 quadrillion, that is very wrong, and the network needs to change rapidly. On the other hand, if the data set is incorrect, it is actually incorrectly labeled as $10 quadrillion, then the outlier suddenly changes the entirety of the neural network. So generally, if there are errors in your data set, you should try to avoid using mean squared error, or as an alternative, use Huber loss, which is basically a mix between the two. You'll notice on the right, it's rounded at the center, but as it goes further away from the center, it becomes a linear scale. Now, the second type of neural network, as we mentioned earlier, is a classification network. And for this type, you generally only want to use cross-entropy loss. It is widely agreed upon to be the best general loss function for classification. There are other niche ones that we won't get into in this presentation. Cross-entropy loss, as you can see here, is a little bit of complex math, but all you really need to know is that it scales the output of a neural network into a probability distribution. So let's come up with an example. Let's say that we're looking at a neural network that is trying to classify handwritten digits into their numbers. So they're given images of people's handwriting, and they try to tell what number it is, if it's a 0, 1, 2, 3, etc. So an example output that you might expect, given the number 0, it would say something like, it is a 94% chance that this input is 0, it is a 5% chance that it's 8, and it's a 1% chance that it's 99, or that it's 9. That's exactly what you would expect, but a raw neural network without this loss function would output 10 arbitrary values that are loosely correlated to probability. So what the loss function does is it scales each of these values such that they all sum up to 1 and can more accurately represent how off it is. So in our given example of 94% chance of it being 0, that number can go up. If it's only 94% sure, why isn't it 100% sure? And that's where the loss is. That's the loss. So the network will be trained to reinforce the belief that that is actually the number 0.
And a little bit about NeuroTech at UCSD. We are affiliated with the international organization NeuroTech X. And here at UCSD, we started in January 2020, so a relatively new club. Our faculty advisor is Vikash Gilja from the TNEL Research Group, which stands for Translational Neural Engineering Lab. And he's a professor in the EC department, working with a lot of invasive neural recordings, trying to build neural prostheses. And also we have connections with Wearable Sensing, which is a San Diego-based headset company that's been kind to support us with many of their hardwares. So if you're interested in doing projects with high quality neural recording devices, we have those and hopefully. And we compete in the annual Student NeuroTech X competition. And this past November, we just submitted our 2020 competition. So we'll be excited to iterate on that and also build more projects in order to compete in future competitions in the spring. Our mission here at UCSD is to bring students together who are interested in neurotechnology to provide a way to get involved in the technology and network with people.
Hey everyone, I'm the president of Triton Robosub, and we build autonomous underwater vehicles. We were founded in 2018, advised by Dr. Ryan Kastner and Dr. Kurt Sugars in CSC and EC, respectively. We're based in C-Lab, which is in CSC 2127, and we compete in an international robotics competition where we build our AUV to complete a series of tasks.